number of talks, all focused on some of the chemistry questions that the origin of life brings to the fore. The first talk is going to be online because the speaker, John Sutherland, was unable to fly here at the last minute, so I'll be speaking.
Recording in progress.
And his talk is going to be on origin of life systems chemistry. And, go ahead. Thank you.
Okay, thanks everybody. Good morning, and my apologies for not being able to be there in person, but I'll do my best to give you a presentation from the UK. So I'm going to talk about origins of life systems chemistry. And what I mean by systems chemistry is the realization that chemistry associated with the origin of life must really be to do with mixtures. Mixtures which have properties which ultimately emerge and give rise to the property we know as life. In the past, I think many of us have focused on individual reactions, but there's been a growing realization over the last 10, 15 years that individual reactions, whilst important, have to be incorporated into an overall network, if you like. So, without any further ado, let me start by considering the sorts of feedstocks you might have available on the early planet, and whether those feedstocks would be suitable for the synthesis of molecules destined to become biological. Now, if you look at these molecules displayed here, the sort of representative examples of biological molecules, you'll notice that they contain multiple carbon atoms bonded to each other, as well as heteroatoms such as oxygen and nitrogen. So the task faced by the synthetic chemist, whilst trying to understand how these molecules might come into existence, is to think of ways in which carbon-carbon bonds could be formed easily, as well as carbon-heteroatom bonds, and to try and get things such that we end up with approximately the right redox state for biology to start. And if you consider carbon in biological molecules, it tends to average an oxidation level around about that of formaldehyde. So it's a crude approximation, it's not desperately important for what follows, but it's roughly the oxidation level of formaldehyde. Whereas if you take nitrogen tends to be at the oxidation level of ammonia. Biology, of course, now accomplishes these two amazing tasks. One of fixing carbon from CO2, and the other of fixing nitrogen from N2. Now, in the early days, of course, fixing one without the other wouldn't have been any good, because biological molecules require for life require both nitrogen and carbon. And so a very, very early assessment, just based upon this kind of analysis, is that if you could use hydrogen cyanide, it has a carbon atom which is close to the oxidation level required, it requires some reduction, and it has a nitrogen which is at the oxidation level. So if you fix hydrogen cyanide, or if you take hydrogen cyanide as a feedstock, you're fixing both carbon and nitrogen, one at the right oxidation level and one at close to the right oxidation level. So that's an important consideration, I think. And just to sort of, if you like, compound that, is the fact that if you start with formaldehyde, you actually have a problem, which is that if you want to join two formaldehyde molecules together, it's like trying to get two north poles of a magnet to come together. It's difficult, because they repel each other. In organic chemistry speak, that means it's difficult, because it means unplugged. In contrast, the addition of hydrogen cyanide to formaldehyde is a very easy reaction. It's the formation of cyanohydrin that occurs spontaneously in water and has a very high equilibrium constant in favour of the formation of the cyanohydrin. So a key observation in our labs here was that you can actually take hydrogen cyanide and reduce it to formaldehyde. And so you don't have to start with formaldehyde and hydrogen cyanide, you start with cyanide and reduce it, and you end up with a mixture of cyanide and formaldehyde. The reduction, it turns out, is best done via two sequential one-electron reduction reactions. And that's because hydrogen cyanide has an innate propensity to undergo a one-electron reduction because of the stability of an intermediate known as an inigural radical. So we generate those electrons by using ultraviolet light to dislodge an electron from a soft anion such as hydrosulfide. The electron, once dislodged, becomes solvated in water. And in conjunction with the proton, either at the same time, electron and coupled electron transfer, sequentially, or after the reaction of the electron with the hydrogen ion to become a hydrogen atom, you get the formation of the imino molecule. This then picks the hydrogen atom, becomes the iminoformaldehyde, this hydrolyzed the formaldehyde, which then in situ reacts to make the sour hydrogen, glycolonitrile. Now this nitrile group is electron withdrawn, so the electron withdrawn substituent next to it, so it too can undergo reduction. And then you hydrolyze the result, and you generate the first homologated compound, the first compound with a carbon-carbon bond at the level of formaldehyde, which is glycolonitrile. Repeat the process and you make glycerol. So the take-home from that is that you take hydrogen cyanide, hydrogen sulfide, optionally a metal such as copper in its oxidation at stage 1, which photoredox cycles between 1 and 2. That facilitates the process. It's not obligatory, but it assists the process. So hydrogen sulfide, hydrogen cyanide, optionally a bit of a transition metal. Irradiated, you make C2 and C3 sugars. You ultimately need to make ribose, this constituent of ribonucleic acid, RNA. Now, if you build on that reaction, you scope it out, you see where would it logically go if you apply it to other substrates that might be available. Then you actually build up a reaction network, and that network of reactions shown here is complex, whatever that means, but it's a network which produces approximately half of the canonical amino acids, produces ribonucleotides, and glycerol, phosphate, lipid precursors. So just to home in on a couple of aspects of that, here's the reaction of hydrogen cyanide to start with, making the 2-carbon sugar, and then the 3-carbon sugar. 2-carbon sugar reacts with cyanide to make a 2-amino-oxazole, which can then undergo CC bond formation with glyceraldehyde. You assemble the ribonucleotides here by a sort of counterintuitive process where you take half a sugar, add half a new nuclear base, add the other half sugar, and then the other half nuclear base. And this gets around the problem of the difficulty of adding a preformed nuclear base to a preformed sugar. So there's a reaction network. It's not complete yet. We're missing still a good route to the purine nucleotides. But we think that the amino acids are probably limited to about half the canonical number because the others actually look more recent by a number of criteria. And so we think that the fact we haven't made them by prebiotic plausible chemistry is probably consistent with the fact that they might not have been or weren't available on the early Earth. So let's now explore some consequences of this. One of the consequences is the need to actually have a geochemically plausible scenario. You present a piece of synthetic chemistry to an audience and ask them to believe that it could have occurred in the early Earth. And they rightfully ask you to explain how could that happen without people in white coats doing all the things that synthetic chemists do, like adding reagents sequentially, purifying products, doing workups and then mixing things together again. And what we've worked out over the years is that the only way we can really think of achieving this is a surface scenario where you have things being dissolved sequentially as streams pass over the surface. So a stream passes over a surface which contains soluble materials, it will in sequence dissolve those. And you can then imagine that equates to the sequential addition of reagents. If the flow of water is limited, then occasionally the solution will get concentrated and crystallization can take place. And if the flow separates the monolithic from the crystal, that gives you a way of purifying materials. And so certain intermediates on the synthesis, for example, of RNA, one of the intermediates is a highly crystalline material, which actually additionally crystallizes in the form of a conglomerate, which offers some interesting opportunities about the potential to resolve it, to generate homochloral or an antinomically pure ribonucleic acid, which would be an important aspect of any early synthesis. So in sum, this is how we think it could have taken place on the Earth. A surface environment, gradual flow of water, and all of the requirements of synthetic chemistry met by this sort of scenario. You couldn't, for example, do this sort of thing in a deep ocean, because the deep ocean would dilute things to a great degree, no opportunity for crystallization, and very difficult to imagine how you could separate the purified units in any other way. Now, another consequence of the production of nucleotides at the same time as amino acids is the suggestion, which I think many of us in the field have felt, which is that RNA chemistry and protein chemistry must be very closely linked. And so that link in modern biology is perhaps strongest when you look at the genetic code and the process of translation. Just as a reminder, the genetic code essentially is written by interaction of an enzyme, amino acid synthetase, both with its cognate amino acid and with its cognate RNA. It recognizes the amino acid because of its specific shape. It recognizes the tRNA by one or two, maybe a few, so-called identity determinants, which specify that that tRNA is destined to become amino acid with a particular amino acid. The amino acid tRNA synthetase then writes the code, makes an amino acid tRNA, and the code is read very simply by Watson-Crick decoding in the 30S subunit of the 30S of the bacterial ribosome, the decoding center of the small subunit of the ribosome. Now, we got drawn into this by thinking, well, if amino acids and nucleotides are produced at the same time, then any attempt at doing RNA replication chemistry would have to contend with the presence of amino acids. And the favorite intermediates for RNA elongation chemistry, imidazolides, are known to react with amino acids, either with the amine at high pHs or with the carboxylate at lower pHs. And so this produces a phosphoramidate, this produces a mixed anhydride. So we've looked at the chemistry of phosphoramidase and mixed anhydrides in detail. And it turns out, long story short, that the chemistry of mixed anhydrides is, I think, very interesting. It turns out that if you make a mixed anhydride between an amino acid and a 5' phosphate of an RNA, which looks like the acceptor stem of an RNA molecule, which is a duplex with a short overhang. If the overhang has the right sequence, it turns out that it can adopt a folded back conformation, which enables the amino acid to be transferred from the 5' phosphate to the diol to make an amino acid ester. And we tested this out using intermediates made by conventional chemistry just to see what would be the consequences. And we immediately got attracted to the idea that there might be some sort of coding, some sort of recognition between the nucleotide sequences and the amino acids. So we first of all decided to do this by high throughput experimentation. We randomized the overhang sequence and used a selection procedure to determine those sequences which were most efficiently underwent the transfer of the amino acid. And what we found was, in conjunction with our investigations group in Heidelberg, that in fact the preferred sequences is the top 10% of preferred sequences, and the sequence, the 100% of all sequences, there was very little difference between the sequence that was preferred to transfer alanine, glycine, proline, valine, or leucine. And so that was somewhat disappointing, but in retrospect, we think not too surprising. And what was interesting was that when we came to then, this is unpublished, but it will soon be published, we then varied the terminal trinucleotide of the stem. We determined in preliminary experiments that the fourth and fifth residues had little effect on chemistry, but the first three did. And we then found that there is a remarkable dependence on the efficiency by which certain amino acids are transferred, and it relates to the terminal trinucleotide sequence. So alanine is best transferred by UA or UUG, glycine by CUC, proline by GCU, and leucine and valine, which are related amino acids, are actually best transferred by related sequences. This is data derived from sequencing. We confirm this by HPLC. You look at the sequence with a trinucleotide CAG, alanine is the best transferred, L is much better transferred than D, so it's stereoselective. Change that trinucleotide, you find a sequence that transfers proline best. Change it again, you find one that transfers leucine best. We're using here a pentanucleotide to do the transfer, but we can do this with a tetranucleotide or even with a trinucleotide. And with a trinucleotide, it turns out the selectivity is even higher. And we think that the evolution of ribosomes could facilitate this being carried out with even smaller phosphorylated and amino-isolated nucleotides, even down to the monomer. Of course, the monomer, the mixed anhydride monomer, is what biology currently uses. So we think this actually explains why in modern biology the identity determinants in tRNAs are still clustered, not just in the anticodon loop, but also in the acceptor state, because that's where they would have first been. It doesn't explain why amino acids are assigned to the codons that they are, and very briefly, we think they're assigned to these codons because of a relationship between binding of occupy the so-called fan boxes, the fourfold degenerate boxes of the genetic code. And those fourfold degenerate boxes are characterized by having an extra hydrogen bond. In the case that they don't have all GC, they have an extra hydrogen bond between the 2' hydroxyl of U33 and the internucleotide phosphate indicated here. And so we thought that would probably mean that the family boxes are those which best associate, most strongly associate with corresponding codons. And it turns out this is the case. We can look at the family box anticodon-codon interactions, they bind very tightly. Non-family box anticodon-codon interactions are approximately 50 to 100 times weaker. And it turns out that if you have two contiguous family box codons on a message, you can actually bind these tRNA anticodon stem loops sequentially all at the same time to that message. So here's one example using biologic interferometry where we combine one anticodon stem loop and then bind the second one, and then unbind the first, unbind the second, and another example where we can do the same. And we think that the reason that the amino acids were first assigned to family box codons is because the tightness of binding of the family box anticodon to the codon would have assisted the process of bringing two tRNAs together. If you bind them onto a message, you're effectively bringing them into the same room, and then all you need to do is bring the 3' ends of amino-isolated tRNAs together to get the proximity required for transpeptidation. So the idea is that the first peptides could only be produced if there was proximity between the two termini, and that the proximity would have been facilitated by having tight binding family box anticodons binding to the corresponding contiguous codons on a piece of message. So there you go. Systems chemistry suggests amino acids and nucleotides will be made together, and the assembly chemistry of nucleotides and amino acids, when viewed together, we think gives you additional benefits and suggests an underpinning of the central part of the central dogma that Francis Crick described, whereby information is transferred from nucleic acids to proteins via translation from the genetic code. So, a long story made short, I apologize for that. I'd just like to say that that actually agrees with some suggestions made by some very smart people a few years back. And to then thank the people in my group who've been responsible for this, those involved, the ones who are still present in my group, those not involved, the ones who also contributed to work I've described, colleagues who assisted, and the funding agencies who supported this. And lastly, I'd like to thank you for your attention.
We obviously have time for questions. I'm going to go first. Down there.
Hi John, this is Anton Petrov from Georgia Tech Atlanta. So I have a question about the second part of your work on genetic code. So if I'm not mistaken, you had a construct in which at the 3' you had 5 nucleotides UUCCA. It appears that in tRNAs there are 4 nucleotides, position 73, discriminator, and then CCA. So can you make any comments on that? Why do you have 5 nucleotides?
Yes, okay. That's a good question, Anton. And we arrived at the 5 nucleotide overhang in a sort of kind of strange way. We, like many others, we subscribe to the opinion that tRNA looks like a product of duplication. But if the tRNA is a duplication product, then 76 residues, which is the canonical length, is 2 times 38. And that places the join in the anticodon loop. And so it also suggests that there would have been a symmetry where the anticodon loop resembled the overhang of the 3' terminus. So the anticodon loop is 7 nucleotides, the canonical overhang is 4, so we went for an overhang of 5 because that suggested we could actually, by small changes, we could either recapitulate the modern overhang or recapitulate the anticodon loop. And we then used sequence comparison between conserved bases in the anticodon loop and the overhang to try and arrive at a consensus sequence that could have given rise to both. And believe it or not, when we tried that first 5-base overhang, we immediately found amino acid transfer. Whereas when we actually use other overhangs, we don't see the same transfer. And a comment on the modern situation, ACCA, that ACCA is often linear conformation, but if you mutated to UCCA, Joseph Puglisi showed many years ago by NMR techniques that the UCCA can adopt a folded back conformation, whereas the ACCA can't. So our overhang has that U in place, basically to give you the if you like, the proto high turn, the U-turn motif, to give you the folded back conformation. So the idea then is that as biology changes over time, you can mutate the overhang, make it 1 base shorter, either by truncating it or elongating the 5', and then you mutate it such that it no longer adopts the fold back conformation.
Yeah, hello, thank you for the talk. So I have 2 questions. The first one is a naive question from an astronomer. Could you explain what is the difference between RNA and tRNA exactly? So that's the first question. And the second question, so you said that the chemical reaction you explained at the very beginning were favored in a surface environment with flow and water, and you said that it could not happen in a deep ocean and thermal vents. And I was wondering, because for these thermal vents we could expect like a porous material with small pockets where you could have some fluid inside, and could this be some way to circumvent the problem of the low concentration and maybe?
Sure.
Yeah. Okay. Thank you.
Okay. Yeah, again, both good questions. The first one, there's no such thing as a naive question. When it comes to this, it's an interdisciplinary topic. We need to communicate with each other. RNA is RNA, and the T, the prefix, simply refers to the fact that it's an RNA molecule which is involved in the translation process, transfer RNA, transfers amino acids. So it's a substrate which just denotes a specialized task for a particular RNA molecule. When it comes to superficial environments versus deep sea environments, I'm an experimentalist, so I'm more convinced by experimental results than theories. And the ideas about chemistry in deep sea vents versus the surface have been bouncing around for a long time. There's plenty of evidence now that you can do sequential reactions in superficial environments, but to my knowledge there is no evidence that you can do this in simulated deep sea environments. So whilst you're right to point out that there are some potential ways in which you can imagine things happening, I think we would all be happier in believing those if there was some experimental demonstration that they could actually take place.
Okay. Actually, I have a quick follow-up question to that, which is, I've heard of it also from a naive perspective. We've heard about the stream idea, at least the principle, several times. Have there been experiments in something like a microfluidic analog of a stream geometry where you mix things and they repeat, we create these intersections, and you do sequential chemistry of the type that you're postulating could have been responsible for doing that in the early Earth?
So we've done some very, I would say, crude and preliminary experiments using flow apparatus that our colleagues in synthetic chemistry use for sequential chemistry like that. They call it in flow. You know, you can argue about just how close to that approximates to the search environment. We would very much like to do this in a more realistic way. There are some safety issues dealing with gaseous HCl and H2S. So you have to build a rig in which you could do this safely. The alternative will close things in tubes and do it by proper microfluidics. But then again, that faces the critique that it's not as close an approximation as one could make. So, short answer, we're getting there, but we haven't yet done it as convincingly as I think we'd like to do it.
Thank you. Next question.
So, hi John, great talk. Here's Thomas Henning from Heidelberg. You started as HCN, and of course that is a wonderful molecule and a key molecule, as we all know. But let's assume for a second that there would not be enough HCN available. So what would be your next best choice?
Hi Thomas, good to hear from you. So, let me turn the question around and say, you know, there are two ways of approaching it. One is to say that planetary science and geochemistry can give us clues about what might have happened. The second is to say that the requirements of chemical synthesis can point to the need for certain materials to have been present. And I would say we've now gotten to the point where, you know, going back to Van Rose's experiments with HCN making adenine, for example, we've now got to the point where I think there's a very substantial body of chemical evidence that fingers HCN so specifically that we as chemists would say HCN had to be there in sufficient abundance to do this. And we then turn the question around to you and say, so please give us ways in which it could have been there. Please suggest to us ways in which it could have been there. You know, we know it can be made during impacts, we know it can be made by lightning, you know, we know it's abundant in the universe, so it could have been delivered early on or could have been subsequently delivered. But please, let's use the chemistry as a clue to sort of persuade people in the planetary science community to come up with even more convincing ways in which we can get to HCN, because doing it without HCN is going to be real tough.
My name is Dimitar Krenev. I want to ask you, you showed very clear stable chemical transfer and amino acylations based on a specific sequence. And this is quite amazing. I mean, lots of scientists dream to show that experimentally, and you show it now. Is there any insight of the mechanism of this stable chemical process? That's my first question.
Oh, Dimitar, that is a really good question, and we have approached a whole series of really good modelers, and they all had a go at this, and they've all come up with suggestions. And to be honest, you know, molecular modeling is powerful now, but it has its limitations, and we just don't know what to believe. We don't see an obvious explanation for ourselves, but the data is real. It's surprising that it's you know, it's in triplicate, it's done by HPLC, you've got, you know, all sorts of additional backup data that suggests the stereoselectivity is real, you know, up to 10 to 1. And so the answer to that question really is, it is a real observation. We cannot easily explain it. We're looking to try and get structural data to explain it, but the compounds involved are fairly labile, and you know, getting them to slide long enough to acquire proper NMR data or crystallographic data is a challenge.
Okay, last question.
Hi John, this is David Catling. So you mentioned in your network for making the monomers that you didn't have a good path to the purines yet. And earlier you just mentioned the work by Juan Oro on adenine, going back to to my mind, you know, I don't know so much about what the problems are with the purines, but could you just talk to that and how you think that could fit in?
Hi David, sure. So I think with the preludes, we assembled the nucleotides half sugar, half base, half sugar, half base. With the purines, you're dead right. There is this real clue in the literature from Final Road that says adenine, which has a constitutional formula H5N5C5, is indeed the pentagon of hydrogens. You can make it by allowing hydrogen cyanide to react. If you take hydrogen cyanide and formaldehyde, you can get really high yields of adenine. And formaldehyde is just the hydration product of cyanide. So adenine looks like a very predisposed molecule. And so we think, we've been thinking this for a long time unsuccessfully, but we think that the answer will lie in adenine alternative and allowing that to intercept the pyrimidine nucleotide synthesis. But we haven't yet achieved this. But we think that the observation of Moreau and those who elaborated on that, we think those are extremely valuable.
Okay. Well, thank you very much again for the talk.